Logic is a language which no one speaks on the planet. And it's very different from a natural language, the languages that we all speak. And it's a formal language, meaning you can determine all the properties of the language based simply on the shapes, the forms of the symbols in the language. That's all you need. So we need to know what are the symbols in this language. Now, remember from last week, what makes logic so extraordinary is that it is a language which abstracts away from almost all content. That's to say, in our natural languages, we have words to talk about the world, the content of the language. And logic abstracts away from just about everything except 5 things: and, or, not, if, then, and if and only if. That's all it needs. It doesn't care what the information is beyond that. Only that you do have information. So you want to acknowledge that you've got information, but logic doesn't care what it is. So we need symbols for the language of sentence logic. So I will be telling you what this language is, what the symbols are in the language of sentence logic. Now, if there's a now we will be translating from English or any natural language into logic. So if there is a sentence in English that has neither and, or, not, if, then, and if and only if there's a sentence that has none of those things in it, let's call it an atomic sentence. So here is an example. Jeff B. is 6 feet tall. That is an atomic sentence, because in that sentence you do not find and, or, not, if, then, and if and only if. And we need symbols to represent atomic sentences. So what we will use are the uppercase letters of the English alphabet. Capital A, capital B, and so on. And they represent atomic sentences. And you can think of these as atoms, atomic sentences as atoms. They're indivisible units, and we don't want to look into them. We don't care what's in them. So this is, in logic, the way of acknowledging that you've got information. Jeff B. is 6 feet tall. I could translate that into the language of sentence logic by the capital letter A. All you will see is the letter A. You have no idea what information that represents. So all you need in logic is that you have information, but it doesn't matter what it is. Now, when you combine sentences using and, or, not, if, then, and if and only if, you get what in logic are called compound sentences. So there's just 2 kinds of sentences in logic: atomic and compound. A compound sentence has at least one of those 5 things in it. An atomic sentence has none of those 5 things in it. So compound sentences are like molecules, where the 5 things are like the binding forces that bind atoms together to form molecules. Anyway, what are these things that stick together the sentences to form compound sentences? Let's give a name to and or not, if then and if and only if. It's a scary name for non-math people. For math people, it's a friendly name. They are called truth functions. They also have other names: logical connectives, logical constants, truth functional connectives. They have many, many different names. The book calls them truth functions, so that's what we'll call them. And they're the glue that's used to glue together sentences to create larger sentences. And in English or any natural language, and or not is used in the same way. It builds larger sentences out of smaller ones. Anyway, we need symbols for this glue, for the truth functions. So for not, the symbol for not will be the squiggle. Or it could just be a straight line. So squiggle or straight line, horizontal line. Okay, the symbol for and will be a dot, a little ball. The symbol for or will be a little wedge. The symbol for if then will be a horseshoe that points to the right. Or half of an ellipse. And the symbol for if and only if will be 3 horizontal trip bars. So it's a triple bar, 3 horizontal lines, one above the other. And those are the symbols for the truth functions. And how to symbolize compound sentences. Well, no, you don't really know how to do that yet, because that's the point of tonight's talk on WIFs, well-formed symbol sequences. Okay, 2 more symbols. The next one, you will see tonight how important it is, and it is one of the most incredible inventions of the human mind, because it allows the human mind to do things that you would think no human mind could do, because our minds are finite. We can't do infinitely many things with our minds. And these symbols allow us to do infinitely many things with a finite mind. Unbelievable. They are called sentence variables. Sentential variables. And we will use lowercase p, q, r for these variables. And they're variables over symbol sequences. Actually, they're going to be variables over a special kind of symbol sequence that we'll learn about very, very soon. So they're not scary. A variable is just a placeholder for a sequence of symbols from the language. Okay, finally, we need parentheses, left and right, and they are essential. Parentheses are essential for doing something, namely disambiguating symbol sequences. What does that mean? Here is a sequence of symbols squiggle A, wedge B. Here is another sequence with parentheses. So, squiggle, left parenthesis, A, wedge B, right parenthesis. Do they say the same thing?
No.
No. They're very different. The first one is where I have squiggled the atomic sentence A and wedged it to B. The second one is where I have taken the compound sentence A wedge B and squiggled that entire sentence. If I didn't have parentheses, I could not do this. All I could do would be to squiggle an individual atomic sentence if I didn't have parentheses. With parentheses, I can squiggle something larger, namely a compound sentence. So that's very important. And we will see later tonight that they also can disambiguate sentences. Once we start talking about the rules for determining which symbol sequences are acceptable and which are not. So that's the language. That's it. Those are all the symbols you have. Nothing more. Very nice. Nice and simple. If you're a programmer and you said, that's it, that's the whole language, you know, you'd think it was nuts that there are so few things. But that's all you'll need. And when we actually do things in logic, we will never use the sentential variables. We'll only be using the atomic sentences, the truth functions, and the parentheses. The sentential variables are used to talk about what we do in logic. But that requires a distinction between a language and a meta-language. What we do inside the language and what we do outside the language in talking about what we do inside the language. And that's the distinction between a language and a meta-language. But it's not in the book, so I'm not going to harp on it because you really don't need to know about it. Okay, now the next thing is which sequences of symbols from this language are acceptable, and the analog of acceptable in a natural language is grammatical, and which are not. And so the basic idea is if a symbol sequence is acceptable, then it's something we can look at and take seriously. If it's not acceptable, you don't even take it seriously. Don't even bother with it. Just toss it out. Like the current occupant of the White House. An unacceptable POTUS. Okay. So, so we need rules for determining which symbol sequences are acceptable and which are not. We can give a name to the acceptable symbol sequences, and this is a name that is standard throughout the world. Acceptable symbol sequences are called WIFs, W-F-F, and that abbreviates, it's an acronym for well-founded formula. Well-founded formula. WIF. Of course, this requires me to say something about formula. All that formula means is symbol sequence. Some people don't like to keep saying symbol sequence, so they use the word formula. Formula is not what you find in chemistry. It's not like, what you need to solve a quadratic equation. It is simply a symbol sequence. So formula is synonymous with symbol sequence. And so we're asking for the well-founded formulas. Yes?
Can you just clarify, because on the text it says well-formed?
Oh, well-formed, yeah, sorry. Yeah. Thank you for making that important. Well-formed formula. Philosophers, we love to use the word foundational, founded by, founding. So, at any rate, well-formed as opposed to well-founded. But they both mean the same thing. But thank you for, making that correction. Yeah, well-formed formula. Okay. So, at any rate, we need rules for determining which are well-formed and which are not. So let's start with rule 1. And any atomic sentence by itself is a WIF. Now this sounds okay, but one problem is, when is a symbol by itself? Okay, suppose I just have capital A on the board. That's clearly by itself, and it's clearly an atomic sentence, so it's a WIF by rule 1. But now if I have another atomic sentence on the board, is A still by itself, or is it no longer by itself? The B is separated from A by about 1.5 feet. Is B by itself and A by itself? Yeah, I agree, it is. But now what happens when we start moving B closer to A? As B starts getting closer to A, it's less clear. Now, if B is right next to A is no longer by itself. And we can all agree to that. But at what point, as we move B to A, does A and B, are they no longer by themselves? There's no clear answer to it. It's a vague question. There's no book or document somewhere in the world that says, when B is so many centimeters from A, then both A and B are no longer by themselves. There's no such thing. So we're already in a problem. We stated a rule, and we don't know how to apply it. Because the phrase by itself is a vague phrase. And there's no, on the face of the earth, there's no resolution for getting rid of the vagueness. That's not to say we couldn't do it. You know, the world could sit down, you know, the people who, all the logic professionals would sit down at some big meeting in some fancy hotel somewhere and agree to win, but it's not worth it. It's not worth it. You'll see as you go through the course, you're not going to have this kind of, there will be a big problem with this. Now, there is a way of solving this in words. Instead of using the phrase by itself, we can use the phrase any atomic sentence in a symbol sequence of length 1 is a whiff. And that gets rid of the phrase by itself and substitutes what sounds like an objectively determinate, non-vague phrase. Symbol sequence of length 1. But in fact, that's no less vague than the phrase by itself. Here is a symbol sequence of length 1 when you just see the letter A. Here's a symbol sequence of length 2, A and B. But if I start moving B farther to the right of A, at what point do I stop having a symbol sequence of length 2 and have instead 2 symbol sequences of length 1? When does that happen? Can't say. So at any rate, just have to accept this. Okay, now comes a big problem. We've taken care of the atomic sentences. Now we have the compound sentences. So we have the 5 truth functions. Yes?
I have a question. Let's say A is by itself. So it will stay by itself unless and until these not, and, or, if, then is used with another letter, right? So, I mean, even if we say that it is by itself and we are considering it as an atom, so by that analogy, if there's no bond between any 2 letters, then it is by itself. So, I mean,
Okay, well we're gonna look now at how to introduce the truth functions. But we have a problem. Okay, so squiggle or a straight horizontal line, they're both okay, but not. I'm lazy, and so I typically just quickly write a horizontal line instead of the squiggle. But here's the problem. If I want to tell you which symbol sequences that have squiggles in them are well formed and which are not, how do I do it? I cannot do it in the following way. I cannot write out every symbol sequence involving the squiggle because there are infinitely many of them. Squiggle A, squiggle, squiggle A, squiggle, squiggle, squiggle A, squiggle, squiggle, squiggle A, and so on. Squiggle A, wedge B, squiggle, squiggle A, wedge B, squiggle, squiggle, squiggle A, wedge B, and so on, and so on, and so on, and so on. Here's our problem. If the only way I can tell you which are the legitimate symbol sequences involving the squiggle is to write them all out, I'll never be able to do it because there are infinitely many, and we are all finite beings, and we cannot complete an infinite task. But here is some, it's like a miracle of the human mind. I can tell you, using two symbols, what are all of the infinitely many symbol sequences involving the squiggle. With just two symbols. Even my feeble mind can grasp these two symbols. And here it is. Squiggle P is a whiff, where P is a sentence variable over whiffs. So P is a variable that takes whiffs. And so what squiggle P says is that if you start with a whiff and squiggle it, the result is a whiff. So let's get an example. Here by rule 1 is a whiff, the letter A, right? This is a whiff. Rule 2 says start with a whiff, P, whatever that is, squiggle it, and the result is a whiff. Is squiggle A whiff?
Yes.
By rule 2, it is. Okay, since squiggle A is a whiff, rule 2 says start with a whiff, which is squiggle A, then squiggle it. Is squiggle A whiff?
Yes.
By rule 2. And one more and then I'll take your question. That squiggle A is a whiff. Thus by rule 2, if I squiggle it, I get squiggle A, and it is a whiff. Yes, what it means. All we are interested in now is form. And is the symbol sequence squiggle A an acceptable form? Yes. Is squiggle A acceptable? Yes. Is squiggle A acceptable? Do not worry about the difference between A and not A, and not A. Don't worry about that. That involves the truth of the sentences, which we're not going to look at when we're only interested in whether a symbol sequence is well formed or not. Truth won't enter the picture until we get to logic, when we're interested in doing something that preserves truth. But right now we're not interested in that. We're just interested in which symbol sequences are grammatically okay. I can say true and false things and they're both grammatically okay. I am standing here right now is grammatically okay. I am not standing here right now is grammatically okay. Only one of those sentences is true, the other one is false. But it doesn't matter, they're both grammatically okay. So let me get back to, as everyone, I have to repeat what I said last week. I'm deaf in my right ear. A very bad accident 20 years ago. Where I was hit by a pickup truck while I was jogging and thrown 65 feet. So I lost my hearing from my right ear, along with balance.
They left that detail out.
So, yeah, so,
I was gonna say, so if it was B squiggle A, that wouldn't be a whiff, right?
is B what?
If it was B squiggle A, and then if it was like squiggle.
Oh, okay, good. Suppose I have the symbol sequence B squiggle A. Is that acceptable or not? We don't know yet. We will soon learn it is not a whiff, but we don't yet know that. Okay, we also need rules for the other 4 truth functions. Now notice the squiggle only governs symbols to its right. The other 4 govern symbols to the left and to the right, and need something on the left and something on the right, A and B. Same thing for the wedge, A, wedge, B. The same thing for if A, then B, or A, horseshoe, B. And the same thing for the triple bar, A, if and only if B. But that's easy, because we've got variables besides P. So rule 3 is P dot Q is a whiff. Rule 5, P horseshoe Q is a whiff. And rule 6, P triple bar Q is a whiff. So let's just take a look at rule 3. Squiggle A dot B, is that a whiff?
Yes.
Okay. Is that a whiff? Who says yes? Who says no? Okay, it is a whiff. And here's how we got it. B is a whiff. A is a whiff. If A is a whiff, squiggle A is a whiff. So whiff dot whiff by rule 3 is a whiff. Rule 3 says P dot Q, which is another way of saying whiff dot whiff. So you can use these rules to take complex symbol sequences and break them down into the simplest components, which are atomic sentences. Okay, we now need to introduce parentheses. And here is an example of an ambiguous symbol sequence. A wedge B dot C. A wedge B dot C is ambiguous because the dot and the wedge require something on their left and something on their right. The problem is, does B go with the wedge or does B go with the dot? If B goes with the wedge, using parentheses, we would have A wedge B parenthesized and dotting that to C. But if B goes with the dot, we would have B dot C parenthesized and that wedge to A. So number 1 is A wedge B parenthesized and then dotted to C. Number 2 is B dot C parenthesized and wedged to A. And 1 is different from 2. So if all you see is A wedge B dot C, that's not a whiff because it's ambiguous. It has two interpretations, 1 and 2. And so you need parentheses to represent each of those interpretations of the symbol sequence A wedge B dot C. And so I'm not going to give you a really fancy Rule 7. Rule 7 will simply state as use parentheses to eliminate ambiguities. If you really wanted to make Rule 7 precise, you would have to talk about how you would determine for every left parenthesis that you found its mate, the right parenthesis. And that gets very complicated when you have very long symbol sequences with subsequences of symbols involving many, many layers of parentheses. So the math students will be happy with this, but the non-math people would not be happy to have a very complex rule that talked about the combinatorics of parentheses, so we're not going to do that. So we'll just leave it as use parentheses to eliminate ambiguities. And we need one more rule because we still have a problem. The problem is the first 7 rules tell us what are whiffs, but there are no rules to tell us what are not whiffs. So that symbol sequence that someone told me about earlier, B squiggle A, we can't say anything about it because none of the rules tell us anything about it. Rules 1 through 7 do not tell us it's a whiff, but that doesn't mean it's not a whiff. So we need a new rule, the last rule, Rule 8. And Rule 8 says anything which is not a whiff by the first 7 rules is not a whiff. So any formula which is not a whiff by rules 1 through 7 is not a whiff. Any formula not a whiff by rules 1 through 7 is not a whiff. Yes?
Is there a way to make like multiple symbols like affect an independent like atomic sentence? Like you know how people say like do this and or something? Like is there like a structure for that?
Yeah, that's something more complex though. And we'll talk about that when we get to truth functions. That's a good question. Yeah, well, how to take, you know, in natural language, like and or. Yeah, we're gonna get to that. But that's off in the future right now. By the way, Rule 8 tells us where this construction, namely, rules 1 through 7 construct a set of symbol sequences called whiffs. And where does that close off? Where does it stop? Rule 8 tells us that. It doesn't say, actually, what the number is. So if you've had a course in algebra, rules 1 through 7 rule. but you don't need to know this. And typically you measure the place where it closes off by a number, either a cardinal number or an ordinal number. In logic, people are favor ordinal numbers to measure where things close off, because ordinal numbers measure not just they don't measure quantity, which is what cardinal numbers measure, but order, the ordering of a sequence of symbols. Anyway, for what it's worth. Many of you will go through life never even having heard of the difference between these two kinds of numbers. Who came into this room knowing the difference between cardinal and ordinal numbers? Who came in not knowing the difference? Okay. It's not an important difference outside of math that I know of, and certain other areas like econometrics, you might find it. Theoretical computer science. Okay. So those are the 8 rules, and we need now to just quickly, and it'll be just a few more minutes, very quickly run through some examples to test our understanding of these rules. Now remember, these are the symbols, capital A, B, C through Z, little p, q, r, squiggle, dot, wedge, horseshoe, triple bar, and parentheses. That's it. So if you see a symbol in a symbol sequence that's not among those symbols, then you cannot have a width. So if I have here's a symbol sequence, A dot B. Is that a width?
Yes.
A is a width, B is a width, so width dot width is width. How about A smiley face B? Is A smiley face B a width? No, because the smiley face is not in the symbols in the language of sentence logic. It was a very popular symbol many, many, many years ago. In the 1980s, computer games were very, very primitive. And they were restricted to something called beer pong, where you batted smiley faces around. That was it. So things have changed for the better. Now you have these computer games that are unbelievable. But in those days, all you had were smiley faces that you batted around. Okay. Here is an important question. When I have squiggle A and I add a squiggle to it, do I need to parenthesize squiggle A? No. You do not, when you add a squiggle to squiggle A, have to parenthesize squiggle A, because there's no ambiguity when you write squiggle, squiggle A. And the reason why is that the squiggle governs everything to the right. There is nothing to the left of a squiggle. You do, however, need parentheses when you want to distinguish between squiggling an atomic sentence versus squiggling a compound sentence. And so that's why squiggle A dot B and squiggle A dot B So squiggle A dot B is different from squiggled parenthesized A dot B. When you parenthesize A dot B and then squiggle it, you're squiggling A dot B. But if you just have squiggle A dot B, then there it's only A that's getting squiggled. The hard part, the only time you'll have a problem with whiffs is where you have long symbol sequences with lots of parentheses. You will not, in this course, encounter those whiffs when you do work in logic. I mean, you will encounter multiple parentheses, but nothing crazy. However, in learning about whiffs, you do need to encounter these long symbol sequences, only for the night. Because otherwise the test would be the quiz would be so easy, you would laugh at me and be angry. You'd be angry that I gave you such an easy quiz. So we need to say something about lengthy symbol sequences involving many layers of parentheses. Now, A wedge B horseshoe D if and only if G wedge H horseshoe I is a lengthy symbol sequence, and you all can know that this symbol sequence is ambiguous. Because there are no parentheses, and I've got 1, 2, 3, 4, 5 truth functions, each of which requires something on the left and something on the right. So this is badly ambiguous. But as I start to add parentheses, it will become hard to say when I have completely disambiguated the symbol sequence. Okay, so I parenthesized A wedge B horseshoe D, and I parenthesized G wedge H horseshoe I. And they are connected by the triple bar. So is A wedge B horseshoe D, is that ambiguous? Yes. And is G wedge H horseshoe I ambiguous?
Yes.
Yes. So it's an ambiguous sequence, triple barred to an ambiguous sequence. So let's try to eliminate that. Okay, in A wedge B horseshoe D, I parenthesize A wedge B. And in G wedge H horseshoe I parenthesized H horseshoe I. So I now have A wedge B parenthesized horseshoe to D, and that's parenthesized, and that's triple barred to G wedge parenthesized H horseshoe I, where G wedge parenthesized H horseshoe I is parenthesized. Is that now ambiguity free?
No.
Are there any ambiguous components or subformulas? No. This is now good. But there's a lot of parentheses to look at. Not a ton, but still enough. And I could easily make it even worse. But you're beginning, to realize that to figure out whether some big symbol sequence is ambiguous or not ambiguous, you have to break it up into its pieces. So you start with this piece, A wedge B. And I can draw a line under that to indicate that it is a width and not ambiguous. And then I have D, put a line under that because that's a width. So I have parenthesized A wedge B, horseshoe to D, and then under that put a line. So that whole thing is a width, ambiguity free. Same thing over here, G, I put a horizontal line under that, and H horseshoe I is ambiguous free. I put a horizontal line under that, and since I'm wedging G to parenthesized H horseshoe I, that's a width ambiguous free. I put a horizontal line under that. And then I've got this width, which is ambiguous free, triple barred to the other width, which is ambiguous free, so I can put a horizontal line under that. And that would be the way I determine that a long symbol sequence is ambiguous free or not. I break it down to its smallest components, put horizontal lines underneath it, and then I work downwards as I work outwards. Work downwards in adding horizontal lines, which indicate ambiguity free. Work outwards from left to right as I consider larger and larger sequences of symbols. I could do this as an algorithm, but I never have because you will not need it. Other than tonight on this quiz. But as I said, this quiz is a special, one-of-a-kind quiz. Well, of course, because it involves whiffs, and you're not going to get any more whiff quizzes. But there's something else that makes it special. You have to take this quiz. If you don't get 100 on it the first time, you have to take it again until you get 100. However, almost everyone will get 100 tonight. That's happened for the last 15 years. But there'll be one or two people who will not get the question involving parentheses. And that's just a matter of, becoming used to dealing with all of those parentheses. So that's it for now.